Ever since humans learned to walk upright, it was our ability to communicate with one another that ensured our position as the dominant species on this planet. Throughout the ages, the communication of ideas between individuals has been responsible for every step, milestone, and breakthrough along the path of our development. But it wasn't until the 19th century that mankind had its first taste of instant long-distance communications in the form of the telegraph and later the telephone. These inventions quickly led to the deployment of hundreds of thousands of miles of copper wire around the world, first in large urban centers and later to smaller towns. By the 1930s and 40s, copper tentacles were beginning to extend to rural communities and farms. As more and more people became connected, the telephone became an indispensable part of everyday life. Transmission lines are analogous to water pipes in the fact that they both carry only a finite amount of traffic. With transmission lines, the measure of information carrying capacity is called bandwidth. In the early telephone days, the general solution to increasing bandwidth was adding more copper wire. However, installing more cable is expensive, so to handle increasing loads while making the most efficient use of existing cabling, methods of combining a number of telephone signals on a single pair of wires were developed. Known as multiplexing, these schemes were applied to the long-haul copper transmission lines of the day, as well as the terrestrial microwave systems that dotted the landscape in the 1950s and 60s. In the 1960s, the widespread use of the transistor produced smaller electronic equipment with lower power consumption that gained great popularity with the public and promised fantastic devices in the future. A number of forward-thinking visionaries realized that this trend would eventually lead to enormous bandwidth demands that would quickly swamp all of the copper, microwave, and even the new satellite systems of the day. Another method of signal transmission would be needed to meet the demand. All electronic means of signal transmission have certain basic similarities. Intelligible information is first impressed or modulated onto a carrier signal, which is then sent over the transmission line. The higher the frequency of the carrier signal, the more information can be carried, and the greater the bandwidth. Light has a frequency in the order of 300 trillion hertz as compared with the few billion offered by microwave and the 500 million offered by radio. Thus, many more channels could be modulated on a beam of light than on the highest frequency microwaves. There were some who believed that transmitting signals on beams of light over thin glass fibers was the best way to obtain the needed bandwidth. However, there were a great many problems to solve first. The idea of guiding beams of light was not new. As early as 1841, scientists were experimenting with the curious properties of light that allowed it to be carried by streams of water as well as glass rods bent into various shapes. Even these early experimenters realized that glass was not very clear, so light would not travel very far within the material. Look into the edge of modern window glass, and you will see the same green color that early experimenters saw over a century and a half ago. This led them to believe that light guiding was merely a parlor trick, and they turned their attentions elsewhere. Besides a lack of clarity, the other major problem with early fibers was that light easily leaked from them, especially where fibers touched or where contamination fouled their surfaces. It wasn't until 1951 that the idea to clad fibers was proposed. This was the conceptual breakthrough that launched modern fiber optics. Some of the first claddings consisted of plastic lacquers, but these early attempts did not work well. Later, techniques for cladding glass fibers with glass were developed that allowed the first commercial use of fiber optics in medical gastroscopes. Throughout the 1960s, progress was slow in producing glasses with the exceptional clarity needed for communications. Work was concentrated on removing the impurities from bulk optical glasses, but with little success. A talented engineer named Charles Cow was the first to lay out the specifications that a practical fiber must meet in order to be useful for communications. Cow calculated the allowable loss of the fiber to be 20 dB per kilometer, which would allow 1% of the light entering the fiber to reach the receiver if it was 1 kilometer away. At the time, this was a challenging target because the best fibers available reduced light intensity by 20 dB over a mere 20 meters. Cow's experiments with pure silica glass produced attenuations of only 5 dB per kilometer, and for the first time, the scientific community realized that communicating over optical fibers might actually work. In 1970, Robert Maurer Peter Schultz, and Donald Keck, 3 scientists working at the Corning Glassworks, made a vital breakthrough. By using vaporized glass and adding a small amount of titanium to a fiber core, they produced a fiber with an attenuation of 17 dB per kilometer, an impressive achievement over previous fibers. Continued work with the vapor deposition process and other dopants reduced this to 4 dB per kilometer by 1972. Throughout the 1970s, work progressed on fiber as well as the lasers and detectors required to build practical transmission systems. By the early 1980s, the first long-haul fiber optic networks were in place, just in time to prove correct the predictions of the visionaries of the 1960s. The advent of the personal computer was about to create bandwidth demands never before imagined.